So it is day 4 of DeepSeek's open source release week, and in keeping with the theme, they have dropped the 4th day's release. However, this is more than just one release. It is actually a combination of a few different pieces which were each uploaded as a separate GitHub repository. So we can just go ahead and actually take a look at them real quick right here. And I do have to apologize. This is probably going to be a super quick video because I'm probably too tired to even be making this video, but I want to get it out because for day 5, who knows what sort of special sauce will be coming out, so I want to be prepared for that. But basically, day 4 is optimized parallelism strategies. So first and foremost, we have DualPipe, which is a bidirectional pipeline parallelism algorithm for computation-communication overlap in V3 R1 training. We have EPLB, which is an expert parallel load balancer for V3-R1. And finally, we have a kind of analysis repository where essentially you can actually see some of the logs and output of these other technologies in process. So you could almost parse those to learn nuances and see actual examples of them in process. So let's first and foremost just kind of go and take a look at DualPipe. So essentially, DualPipe is a way to actually have overlap of forward and backward computation to communication phases, reducing pipeline bubbles, which are basically just like when certain aspects of the computational process are not being utilized. So that's kind of like inefficient, if you will, which is obviously the whole theme of this week's release, which is just increasing efficiency to boost cost effectiveness, performance, etc. And we can see here there is kind of a little graph where they actually show the overlapped forward and backwards, which are denoted by the yellow/green combined. So basically like everything like from here to over here. However, the graph isn't really what I want to focus on. What I want to actually look at is that this was introduced in the DeepSeek V3 technical report. And if we go and actually look at that paper right here, we will actually see where they talk about that. So in order to facilitate the efficient training of DeepSeek V3, they implemented meticulous engineering optimizations. First, they designed the DualPipe algorithm for efficient pipeline parallelism compared with existing methods. It has fewer pipeline bubbles, which means it has fewer moments where things are not being utilized, so it is more efficient. It overlaps the computation and communication phases across forward and backward processes, thereby addressing the challenge of heavy communication overhead introduced by cross-node expert parallelism. So basically what this does is it allows different things to happen in overlapping time segments, I suppose you could say unscientifically. But basically, these are things that otherwise would have perhaps had to wait for one or the other to complete before then proceeding. But what they've done is like timed it well and optimized so that these different things can actually occur in overlapping time segments, therefore at the same time. Now, something I think that's kind of interesting about this that made me like, I suppose curious you could say, is somewhere down here they actually say that although DualPipe requires keeping 2 copies of the model parameters, this does not significantly increase the memory consumption since we use a large EP size during training. And if you kind of remember day 2, we had the deep EP right here, which was the kind of kernel special tweak with the PTX out of dock tweak that they had down here and things like that. So essentially, it actually keeps 2 copies of the model parameters to do this. And from my understanding, the reason that there are 2 copies of the parameter is because the forward pass and the backward pass may actually be modifying the same parameters at the same time. So having 2 copies of them kind of allows that to occur. All right, so the other one is EPLB, where if we click on this real quick, it is Expert Parallelism Load Balancer. So expert parallelism, of course, relates to mixture of experts, models, and things like that. So essentially, okay, when using EP, different experts are assigned to different GPUs. Because the load of different experts may vary depending on the workload, it's important to keep the load of different GPUs balanced. As described in the DeepSeek V3 paper, they adopt a redundant expert strategy that duplicates heavy loaded experts. Then, with heuristically pack the experts to GPUs to ensure load balancing across different ones. They attempt to place the experts of the same group on the same node to reduce internode data traffic. So basically like keeping everything within the same like NV-linked server, I believe, instead of having to send it to the other servers through InfiniBand or something like that. But really what I find very interesting right here is they talk about how they actually do this. And I do believe I had read that like the DeepSeek crew had a quantitative like trading investment background or something like that. And I find this paragraph here very interesting because they open source the load balancing algorithm. The algorithm computes a balanced expert replication and placement plan based on estimated expert loads. Note, the exact method to predict the loads of experts is out of this repo scope, but then they say a common method is to use moving average of historical statistics. And this is something very interesting because if you actually just copy paste this and Google search this term right here, it's going to be entirely stock related. So moving average is kind of like a very commonly referenced like trade signal. So people use the moving average to kind of guide their decisions whether to buy, sell, or hold a stock and try to kind of predict which way it's going to go. So this is almost seemingly like implementing some form of like predictive analysis based off of like actual like stock tricks and things like that. So if we scroll down one more time, we can actually see an example of this, which is kind of cool, but it can perhaps seem a little confusing as well. So basically each layer, okay, so this is a 2-layer MoE model. Each layer contains 12 experts, and they introduce 4 redundant experts per layer, depending on this algorithm that kind of figures out which experts need to be replicated so that the load does not become unbalanced. So basically we can see right here that this tensor starts at 0. So this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And 0 to 11 is obviously 12. So that just for that 12 number to make sense. But we can basically see here, like the actual number that shows up in this little graph down here will actually be replicated for the one that has a high load. So the higher the number here, we can think of just as like the higher the load for that expert. So in this kind of first layer right here, we can see, okay, that's 0. So 1 would probably want to be replicated as well as 2, 3, and 5, and then 6, 7, 8, 9, 10. So 1, 5, and 10 would probably be replicated because those would be the ones that kind of needed the most resource to keep everything balanced. So we can see 5 here is replicated. We have 4 is replicated as well. So that would be this one. Okay, so that is confusing to me, but I suppose it makes sense. And then 10 is right here. We can see. So 10 is replicated. Oh, and then 1 is replicated as well. So again, very unscientific, but basically this is just showing us very simply how this load balancing policy will kind of replicate the specific experts that are under heavier load in order to try to keep everything balanced. And that's like pretty much the gist of this specific expert parallelism load balancer. The final of the 3 repositories here we see are the profile data, which is just basically the data that comes from the different, like, okay, so we can see this data was captured using the PyTorch profiler. So this helps the community better understand the communication to computation overlap strategies and low-level implementation details. The profiling data was captured using the PyTorch profiler. So this is almost like log output that you can actually then go through and actually see how these implementations were happening during the actual training of the V3 model and things of that sort. All right, so I've downloaded Chrome and gone to the Chrome://tracing page. So if we just download some of this data right here, we will actually be able to see it in a cool, kind of visually, aesthetically pleasing and understandable way. So I will just kind of go ahead and download this. And then once we have downloaded it, we can actually go ahead and load it into the Chrome browser from our download section. And this will actually kind of allow us to see the actual data just like this. So these are kind of like training logs. Now, truth be told, I'm not very like good at using this tool right here. So would have to apologize about that, but you can kind of see, you can drag and drop, you can click on different things. And essentially, I do believe kind of the whole gist of this is to actually be able to see the computation to communication overlap in actual implementation here, as these are kind of logs from like a training session where that was actually implemented. So, all right, I do apologize. This was probably a rather lackluster video. I try to always put a lot of effort and like high quality preparation into my videos. For this one, I just truthfully am like, I'm exhausted. So I wanted to get this out just for consistency and continuity. And again, if I were to really summarize kind of today's drop, it is really, again, just about optimization and efficiency. So the actual overlap there is really quite interesting, and it's not necessarily, I guess, something I really did justice to actually explaining, but I guess we could say, so real quick, kind of as the outro, but also kind of to give a little more insight. Imagine we had like a single lane road like this, and there were cars coming from either direction. So normally the cars would have to yield, and then the ones that were going in one direction would go, and then those would stop, and the ones going in the other direction would go. It's almost like that overlap is still having cars in opposite directions on the same road, but it's almost like you've perfectly timed them to actually be able to like kind of turn around each other completely in sync. So like it almost reminds you of like a helix pattern for like DNA, but like it's almost like really finely orchestrating the timing to allow for multiple things to occur at the same time, I guess you could say. And that's kind of what the DualPipe is really doing. And I think that is really very interesting, and likely more than I let on with my perhaps lower energy coverage of this specific day. But again, I did just want to get this out because I've committed to doing this, and tomorrow or today will be the final drop, and I look forward to seeing what it is. So thanks if you watched this video. Take it easy on me in the comments, because I wasn't all there for this one. So thanks for watching.